So now we will go for the complexity analysis of another famous sorting technique, that is what we call quick sort. Now from this sorting algorithm, I hope you will understand whether this sorting algorithm is really quickest or not. In previous case, that is in the merge sort algorithm, we have already seen that it takes big O of n log n, the class of function is n log n, for sorting data in both in worst case and in case of best case. Now it is not same present in quicksort. And what quicksort say? Quicksort actually have an algorithm something like, we have an entire data set, we consider one of them as pivot element, and we start journey with two pointers present here and here. Suppose this is P and Q. P goes in this direction and Q goes in this direction. Depends on some criteria, P stops, and for opposite criteria Q stops, and then we have an exchange between the value pointed by P and Q, and then it continues. So P and Q, basically our goal is to somehow keep this P and Q closer and closer, and a time will come when we see that P and Q has crossed each other, and then they stopped. They When P and Q stop crossed each other, we don't have any exchange of the value pointed by P and Q. Rather, we have a situation, assume that this is the location where Q has stopped, and somehow P has crossed somewhere and P stopped here at the end. So when we find that P has crossed Q, we stopped, and we have an exchange between data pointed by pointed by Q with data pointed by the pivot. And then what we have seen? We have seen that after swapping the data set that is generated, we found that the pivot element present in the first location actually placed in its correct location with respect to the sorted array. What I mean, suppose the data set is given something like 4 2 8 1 6 3, something like this. I'm not going in exact detail of P and Q, but somehow with respect to the original array, 4 should be in its fourth place, because with respect to the sorted array, the sorted array will be something like 1 2 3 4 6 8. So 4 should be in a fourth position. So after doing all these things that we have discussed, we will see that 4 already in its correct position with respect to the original array. Whatever data present before 4 are all lesser than 4. Whatever data present after 4 are all greater than 4. So this 1 2 3 is present somewhere over here. May not be in this order, maybe in some another order, but they will be present, only they. And in this side we will see only 6 and 8 is present in some order. Now since 4th is already placed in its correct position with respect to the original sorted array, that is why when we divided the array into two parts, we have seen that we don't involve the pivot element. In case of merge sort, the division was from lower to middle and middle plus 1 to upper. It was something like that. If you are able to remember, I hope you can understand. But in case of quicksort, if you remember, the division was from lower to middle minus 1. I mean not middle, some pivot, I mean the element value, location minus 1 and the pivot element location plus 1 to upper. I am not involving pivot element location because 4 is already placed in its correct position. I don't need to touch it. So what is the basic difference with respect to merge sort? The first visible difference we can see is that in case of merge sort, the division of the two array is blindly. It's exactly always by 2. But here the division is not blind. Here we have an intelligent algorithm in case of quicksort which finds the correct position of the pivot element and with respect to that it divides. Now since it happens, that's why what is the pivot element, that's going to be very vital over here. What I mean to say is that if I assume the pivot element is the pivot element value is exactly the middle value of the original array, I mean the set of data that is present as an input, among the set of data, whatever should be the middle, for example in this case 4 should be the middle with respect to the original array. If this is present in the pivot element, then this division is almost same as merge sort. Why? Because that means time taken to sort n data will be equal to, obviously time taken to sort this half and this half, so 2tn by 2 must be there. But one more thing will be there, that is, to do this we have to traverse this P and Q. There was a algorithm, there was a loop that runs sometimes for changing the position of P as well as position of P as position of Q. And as a whole, if the total number of data is n, we can say that the total journey of P and Q is almost n. I mean, if I start journey from P here and start journey from Q here, so as a whole, since they are coming closer and closer, so total journey, if you compare total number of uh, changes of these variables P and Q will be equal to almost same total array length. So for that we must write n. Now if the equation become like this, naturally from our past experience on merge sort, where we have seen like this one, the same expression I am getting. So naturally I can say that this will lead to 4tn by 4 plus 2n. Similarly, it will lead to 8tn by 8 plus 3n, and naturally ultimately it will become same as 2 to the power I t n by 2 to the power I plus in, which will basically lead to n into t of 1 that we have seen over here. I hope you can remember this part. This, due to this explanation, ultimately I can say that I will be equal to log n. I'm not going to, repeat the same derivation because ultimately they are same, and here it will become n log n, and from where I can say that Tn will be order of n log n for quicksort also. But question is that this is which case? This is complexity of quicksort for a best case. Why I am saying best case? The reason is that, as I told you, that the pivot element value is very vital. Now let's take another example and let's try to realize why it is so vital. Suppose the data set is given something like maybe 8, okay, 8 2 6 3 7 1 5. Suppose the data set is this and you have to sort them. You will see that I'm not going in detail how P and Q will change. This is my pivot element, right? And obviously P will start from here and Q will start from here. Now naturally this pivot, I'm not going in detail how P and Q will change, but one thing I can say that the original sorted array will be something like 1 2 3 sorry 3 5 6 7 and 8. And what is the position of 8 in the original sorted array? Is last one. That means somehow after the first iteration the 8 will come here, and in this side 1 2 7 will be present in some order, and I will have nothing over here. This is blank, and this side contain n minus 1 data. If I consider total n number of data I had in this situation, here we have n by 2 amount of data and here we have n by 2 amount of data in a best situation, almost nearly equal to n by 2. But in this situation, what you can see, you will see that I will have n minus 1 amount of data and there is nothing, 0. So basically if you try to write the relation over there, T of n will be equal to not 2Tn by 2. It will become T of n minus 1 plus n. Naturally, what about T of n minus 1? In this situation, if I assume in the worst situation, if the data set contain whatever the first value is 7 somehow, suppose that this 1 to 7 in some order, and suppose 7 came here. So naturally next time also your division will be n minus 2 in one side, 7 is present in this set and there is nothing here, nothing is present. So n minus 2 data will left to sort. So you can say that T of n minus 1 can be written as T of n minus 2 plus n minus 1 and plus n. If you follow this pattern, next time it will become T of n minus 3 for sorting this n minus 2 part. T of n minus 3 plus n minus 2 plus n minus 1 plus n minus plus n. Naturally, these two things will be there. So, if you follow this pattern, what will happen? Ultimately, a time will come when n minus 1 will work, right? So when n minus 1 will come, and this side you can rewrite in a form n plus n minus 2 plus n minus 3, sorry, n minus 1, sorry, plus n minus 2 plus n minus 2 plus n minus 1, and ultimately what I will get? T of n, I'm sorry, I will ultimately get from this equation T of n will be equal to, this is n minus 1. Naturally n and n will get cancelled and 1 will left. So it is T of 1 basically. Fine. So if we have only one element, how much time it will take to sort, I know this. But in the other side we have this equation. And here you see n minus n will get cancelled out and 1 will left. Here also n minus n will get cancelled out, 2 will left. And it will obviously plus 2 because minus is there. So that means this part I can write something like n plus n minus 1 plus n minus 2 plus plus basically 3 plus 2 plus 1. So we are getting a pattern for this part. This is constant. So constant is not part of discussion. Constant is not depend upon n. But this will depend. And we know that 1, 1 plus 2 plus 3 plus n, this is equal to n into n minus 1 by 2. This is equal to n into n minus 1 by 2. We know this. So that means T of n will ultimately become some constant plus n into n minus 1 by 2. So forget about constant right now. I don't need to, I can say it's almost equal to, forget about constant, it is n by 2 plus, I'm sorry, minus n square by 2. I'm sorry, I had a mistake. Just a minute. Yes, yes, yes. Yes, yes. Yes, yes. I know I had a mistake. So I can say as a almost equal to n square by 2 minus n by 2. So naturally with this equation, this term is dominating the other term because it has a quadratic term. So that's why from this example, and obviously you can say that T of n, that means you can say big O of n square by 2, and naturally 2 is constant, so I will not keep this 2 because for a very, when n tends to infinity, as n tends to infinity, 2 is negligible. So you can say that T of n, that means T of n will be equal to big O of n square, and this is actually the worst case of quicksort. So one thing we have found here is that where you are taking the pivot element, that is not important. If you consider pivot element maybe in the middle, maybe in this right side, doesn't matter. The important is that what is the value of the pivot element. So this is a very important observation we can conclude over here. Is that first one, in best case merge sort equivalent to quick sort. In worst case merge sort is better than quick sort. Third, in worst case quick sort is equivalent to bubble selection and insertion sort. Fourth point, the performance of quick sort does not depend upon the position of pivot element. So these are the important observations we have found, right?